Okay, ready to start? I'm gonna go live. Okay, ready to start? I'm gonna go live.
Shoot.
Hello, everyone. Welcome to today's episode of Corecast. I am your host, Tim.
I'm Mikey.
Sile, welcome everybody to a brand new exciting episode of Courtcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, we do this every 5 p.m. Tuesday, every 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode. All right, so let's get to it. So I guess in coming up with this episode, I want to lay the groundwork for what we'll eventually talk about. Want to start off by talking about information. So we hear about information in the context of computers, data and whatnot. I guess, Tim, I want to, ask you very point blank, how does physics think about information? It's similar to like, how I think about information in a computer science point of view, or like, what are your thoughts?
Yeah, I think information is so important, and it's because one of the most sacred laws in physics, and in many episodes back. So, of course, people know that um, people are very familiar with the concept of energy. Energy cannot be destroyed, or it can only be converted from one form to another. But it turns out that energy is actually not conserved because of this expansion of the universe. And because we don't really know the fundamental laws of physics, any time when something doesn't change, it becomes hugely important. So, so it's important to find something else that's kind of like energy that truly does not increase or decrease, remain the same. And it turns out that that object is information, or more precisely, quantum information. And information is linked to everything that we do. The stuff in front of us, the screen, the fact that we're chatting, or just the fact that things are happening, has to deal with information being exchanged, being modified in some ways. But of course, we don't know. We don't really have a 100% known theory of quantum gravity. So that's why. But since we know that information is conserved, it gives us a handle to try to make an educated guess on how things work. So that's why information is so critically important in physics.
Anything you want to add to that, Mikey?
Um, yeah, I guess just the fact that we talk about conservation of energy, right? But it's almost like you can use energy to encode information, right? Like you can use the amount of energy that a particle has as like a unit of information, if you will, like a bit, like a zero or a one. Like um so in a sense, like conservation of information is almost like the more fundamental um or information is almost like the more fundamental quantity compared to energy. And as Tim mentioned, we all learned that energy is conserved, and it is for the most part, unless you consider an expanding universe. But yeah, really the fundamental quantity, and this has only been appreciated in the last like 10 or 15 years, I would say, realizing that conservation of information is the more fundamental law compared to conservation of energy.
Gotcha. So we've talked about why information is important, but I still feel like I don't know if the audience understands what information actually is. Is it like um I know like classically it's the number of yes no questions you need to answer to specify the state of a system, as it's done in units of bits. But physics wise, like, how is it the same thing, or like, I mean, how do I think about it quantum mechanically? Is such a thing as a quantum mechanical yes no type of question? Like, yeah, how do I make of that? Like, what does it mean when I say there are like, 5 units of information in this object? Like, yeah, how much information does an electron have? I want to give the audience like some like groundwork, or like kind of to wrap their arms around it. So let's be more specific about what information actually is.
Maybe I can take a stab at this. So the preservation of quantum information comes with many names. One of them, one of the alternative name is unitarity. It's a little technical. But it's just the idea that when you sum all the possibilities together, the sum of all of them has to be 1. Right? Like if I roll a die, it can be 1, 2, 3, 4, 5, 6. I don't care how rigged the die is, right? But the possibility is 1, 2, 3, 4, 5, 6. You know, and that holds true in all systems in quantum physics. So we all know that quantum physics is uncertain. It's probabilistic. So for example, I don't know, the atoms in my finger could go up, down, left, right, front, back, right? We all know that logic will tell us that all those possibility has to add up to 1. That's what it really means. I mean, if my finger could just disappear, let's say there's an extra possibility. Well, once we include it, maybe 20%, maybe there's a 0.001% of the time that could happen. It still should add up to 1. So in a layman perspective, one way to think about it is that the preservation of information is the preservation of the possibilities. All the possibilities since the beginning of the universe exist, and they will always exist as part of the universe.
Yeah, actually, that's interesting. So, I mean, what you're saying follows from like essentially seems like from probability theory that when you take the probability of all events and you sum them, it equals 1, saying that like you basically have covered all possibilities. Um, and so one of my questions, like, how do I think about that from like the state of the beginning of the universe to now? Like, clear, I mean, when I say beginning, I mean at the time of the Big Bang when the first photon came out and you had a sense of like what you could observe things via light. um that universe seems very different than the universe now. So what do you mean like all possibilities are like preserved? It seems like, for at least from my perspective, that like things have grown more complex. Seems like the number of possibilities has like increased, but what you're saying with this is that actually has not increased, it's remained the same. So how can I think about that?
Yeah, I think part of it is this issue of measurement, and I think a lot of times in articles and people make it way too complicated.
Mhm.
One of the reasons is just sort of like an observer bias, right? Because we live in this universe, we can only observe one possibility. Like I can't be in different parts of the universe to see everything happening. So maybe
Mhm.
to us, we only see one possibility, but we know that from quantum physics, all the possibility exists and still remains in this universe. But because of an observer bias, we can only see one of them, and that's why maybe we see this particular way the way universe evolves.
Wait, so Tim, let me. Is this the correct way to think about what you're saying here? Is like let's like just like Hill mentioned, the beginning of the universe, we just have gas of random particles, right? There still is the probability that Tim could pop out of the closet in that universe, right? It just that probability is still there. It's just exponentially small, right?
Yep,
Is
yep,
that
yep.
okay? Yeah.
Yeah, and I think it's a little non-intuitive because actually, when we think about normal probability theory, information actually is not preserved, and that's not intuitive because, like for example, if I flip a coin and I flip heads, now when we go back, we know that hey, it's actually not 50-50 heads, it's 100% head because I got a head. So when I think of it that way, the possibility of tails is lost. It's permanently lost. But quantum physics tells us that no. Even though you've only experienced heads, the possibility of tails still remains, even though this is what we observe. There's still a very low probability, or maybe there's a multiverse. If you use the multiverse interpretation, maybe there's a parallel universe in this viewpoint that, hey, I actually got tails. And that still is part of the quantum mechanical universe. Although we can't access it, it's still there.
That makes sense. I can understand that. I guess so in the interest of time, I wanted to segue our discussion over to computation because I feel like information is not complete as a discussion without computation. Like at least from a computer science point of view, move information about and that forms some kind of computation. So how can I tie this back to physics? I guess, Mikey, I'm gonna put you on the spot for this time.
How does computation tie back to physics?
Yeah, like how do I think about computation in terms of physics? Because we've described this object called information or this quantity or metric or whatever you want to call it, called information that seems really fundamental. And it seems like it has some analogs to like computers. So from that perspective, like how do you think about computation? How can you describe it from a physics point of view?
Oh, that's tough. I mean, okay, so I think there is a way to think about everything that happens in the universe as a computation, right? Like, let's say that, typically when we think of a computation, we think of like 1 plus 1. What is that? That's 2, right? That's a simple computation, where 2 is the answer, and the question is, what is 1 plus 1?
Hmm.
We could also think of a scenario where the answer to the question is Tim, right?
Hmm.
And how do you what is the question to that? You could think of that as maybe like all the particles that make up Tim's body, they all add up to Tim, and that kind of evolution, you can kind of think about it like, what is 1 plus 1? You can think of that as an evolution into an answer too. You can also think about like all these particles that existed at the beginning of the universe are moving along their different trajectories, to produce some answer, which is Tim. So the evolution of like particles in the universe can be thought of as a kind of computation.
Hmm.
I think that's kind of where information and physics, at least in my head, kind of come together into this analogy that we're trying to describe.
Gotcha, gotcha. Tim, anything you want to add to that?
No, I think that is exactly what it is. Like the way humans build computer, we actually leverage physics to build us computers.
Mhm.
So physics is the ultimate computer. Anytime if something happens, a computation is done, and that's a very bare bone way of thinking about physics. Like forget about equations, forget about everything.
Mhm.
Computations are happening.
Huh.
Yeah, it's like an algorithm, right? What is an algorithm? An algorithm is a recipe for taking some component parts and creating some entity that someone considers useful, right? And that's kind of what the universe does, right?
I mean, now we've brought in the term useful. I guess like is the
Yeah.
universe doing anything useful? This is the
Well, that's
question.
definitely that's in the eye of the beholder. Um,
Gotcha. I know
well,
Tim, you have some thoughts, but we can maybe save them for a little bit later. Yeah, so I guess Tim, next question for you is I guess we've described information, we described computation, and these tie very nicely to a computer and describe physics analogs for this. So what object in the universe would you say comes closest to that of a computer? Is it like an actual computer or like would the Earth computing things like the sun? What do you think?
So yeah, so if you think of it this way, there are a lot of objects in the universe, um, but unfortunately, a lot of systems are what we call open systems. Things come
Mhm.
in and out, right? And when we think of a computer, we tend to think of them as an isolated system. Like a piece of, I don't know. If you look at your laptop, or your desktop, right? It's not like information are constantly getting into it. Of course, you can go to the internet, you can plug it into things, but most of the time, your laptop, your desktop doesn't change that much. But
Mhm.
but I guess the one unfamiliar thing is that in most physical systems, that's not true. Like the gas molecules in my room, gas enter in and out, and it's very messy, right? Um,
Mhm.
so I would say the closest thing that resembles some kind of isolated computer, other than man-made system, is something that is almost like impenetrable, something that has a really strong barriers to stuff, at least somewhat of a barrier for things coming in and out. Um, and if you follow that logic, it turns out that gravity is uniquely positioned to create these objects. And we talk about them many, many times. Relativity is able to create a lot of barriers because of speed of light, right? There's a finite, information can only travel at the speed of light. So this creates barriers, and of course, the most dramatic barrier of all is the event horizon of a black hole. I think from that angle, and for modern physics, that's probably one of the closest thing to like a computer, I would say. That's not
Huh.
man-made, anyhow.
Um,
Information does leak out of computers, though, right? That's how you do like side channel attacks, and you can hack into someone's computer by trying to like look at the radiation that it gives off. Yeah, but yeah, I would agree with Tim. Like, you could think of the Earth as a fair analog for a computer. Information is leaking off of the Earth, um, in kind of the same way it leaks off of a computer. I mean, yeah, but black holes, sure, yeah, that works too.
I guess it seems initially unintuitive, at least to me, to because black holes seem like, I don't know, these things that like things go, things if they come in, if they go in, they never come out. I mean, there's a whole black hole information paradox that we can cover in like another episode. But I mean, like I guess like I'm still trying to like piece together, how is a black hole doing a computation like what is it actually like doing? I guess Tim, can you elaborate further on that?
I would say one of the dumbest computation in the universe is just existing, right? Like my hand exists, and the fact that it exists in space time, that's not obvious, right? And like
Hmm.
if you imagine the space time as kind of like a circuit in some ways, I think we done an episode a long while back.
Mhm.
It's kind of like my hand, my body, like the screen that's in front of us. It kind of exists in this circuit in some weird way, although fundamentally we don't exactly know how. But like when things happen to them, it's like computation is being applied. So and it's all, and also another thing that's not obvious, right? Like the fact that existence is consistent in some ways.
Hmm.
Like my hand, like this no, the notion that my hand is here and you can slowly move it and it doesn't just explode into bits and like vaporize, from time to time, that it continue to exist in space and time. That's not obvious. So that requires some, pretty heavy computation, I would say.
Hmm. I mean, couldn't you then say like space time itself is a computer rather than just a black hole at that point?
No, I would say
Indeed, people
absolutely.
do
Yeah,
that.
I think exactly. Indeed, it's true, right? But a black hole is just a lot denser. Like imagine you pack a lot of stuff. Imagine you want to expose the computational nature of space time. You
Hmm.
know, like no ordinary space time doesn't have a lot of stuff in it, so you
Hmm.
wouldn't really see the computational nature. So you want to pack more and more stuff in it. Like maybe a star is a reasonable computer, right? Nuclear reactions are happening. But that's
Hmm.
still not enough stuff, right? You want to pack the maximum amount of stuff in it to see, to kind of see all the bits in here and there to see what's happening. So that's why people study black holes,
Hmm.
in those instances.
How does a black hole reveal the computational nature of space-time? I guess maybe that's one question that comes to mind as you talk about this.
Yeah, I think to talk about it, I think we have to first understand some subtleties about quantum physics.
Hmm.
So quantum. So a lot of times when we think about computation, we think about classical computation, right?
Hmm.
And classical computation is a little different from quantum computation. In classical
Okay.
computer, you have like memory, you have a CPU, right? And the way you
Hmm.
compute is like, hey, like let's say you want to compute one plus one equals to two. What you do is you take one, copy to memory, and then some CPU will, I don't know, it goes to some circuitry, and that one gets modified, and you add another one to it. And then you might get
Hmm.
an answer two somewhere, and that two get copied somewhere else, and the two spits out on the screen, and now you know it's two, right?
Hmm.
But quantum computation doesn't work like that. I think Michael, you're
Hmm.
a little more familiar. Like quantum computation is less. In fact, quantum computation has a lot of restriction, I believe, and it's you can't just copy it left and right and just spit out an answer like that. It's more intricate.
The thing that they have in common, though, is right, like when you say one, right, like you set up some system, some circuitry to represent this piece of information that we intuitively call a one, and that might be like some kind of like oh shit, I don't how is that stored in a regular computer? But the
Um,
point is that like we have these concepts that are familiar to us, like one, right? The number one, but that's actually stored as some configuration in a circuit. Um, and then what does a regular computer do? It takes this configuration that represents a one, and it takes another similar configuration that represents another one. It combines them and turns them into some other representation configuration that represents what we intuitively understand to be a two. Um, and that part is common between classical and quantum computers. I think what Tim is alluding to is something deeper than that. Uh, and yeah, I don't know. In my head, I always like to think of quantum operations as closely analogous to classical computations as I can. So I don't know if yeah, how is it different?
Well, I think maybe a lot of people might not be familiar with this, but in quantum computer, information is the first class citizen. And I think one of the problem with quantum computing is that quantum physics has some restriction because we remember we say that information is preserved. That means you cannot really copy your information. You cannot delete your information. Um, and that means and this law is very common in quantum physics. It's like if you have a quantum system and you try to observe it, the act of observing it actually can disrupt the system. And it's precisely because of the preservation of information. So in order for you to compute, in order for you to see things, the input itself has to be disrupted in a, I guess, almost irrecoverable way. But somehow quantum computer, you have to use a lot of intelligent, very smart algorithm to be able to kind of get the right answer out of it. I guess that's one of the subtleties that's a little different, right? Like you can't just have a quantum memory like you have normal memory. You can't just copy.
mhm.
A similar
But
concept exists in regular computers, though. Like reversible computing. There's a whole class people study these reversible algorithms, and that's kind of like quantum computing. It requires some extra restrictions, as Tim said. But like you can set up a classical computer to make it completely reversible. And yeah, that's kind of similar to quantum computing.
yeah, Mikey, to answer, one of the audience members said to answer your question about how 1 + 1 = 2 on a computer, one is stored in a register, and then another one is stored in another register and sent to a arithmetic logical unit to a computer and stored in a third register.
Hmm.
So I don't know if that helps elucidate your confusion from earlier, but yeah. Okay, so I kind of want to take a step back and sort of navigate where we're going in this conversation. So we first talked about information, and we talked about computation. Then those two have, very close analogies to classical computers from a physics standpoint. And as you're mentioning, Tim, we build computers from physics, so there's definitely a close connection there. And then we talked about black holes being basically exposing the computational nature of space-time, I guess. And then we now took another leap and said that space-time itself can be thought of as a computer. Now, based on the title of this episode, we talked about self-correction. And self-correction to me involves something with error correction, because I assume when you're self-correcting, what are you correcting? You're correcting errors. So can we describe at a high level what error correction is, and then like kind of go into what quantum error correction is, at a reasonable level, and then we can tie it back to this. So I guess, Mikey, I'm going to put you on the spot again.
Yeah, I mean, so I think this idea of error correction is something that people don't think about a lot when they think about computers. It's like when you load up the calculator app on your Windows computer and you put in 1 + 1, it's always going to give you the answer 2 in a very reliable way. And I think what a lot of people don't know is that the fact that computers are reliable should not be taken for granted. Um, Electrical systems are highly unreliable machines. They're very unpredictable. They're subject to a lot of noise. So the fact that the computer gives you the same answer every single time you ask it a question is actually one of the great feats of modern computer engineering. And a lot of this comes back to this dude named Claude Shannon. That's his first name, right? Claude?
Yeah.
Yeah, I think so. Okay, yeah. So Claude Shannon, I forget when it was, like in the 30s, 40s, 50s, something like that. He basically invented the modern notion of digital. And we usually think of like digital as like, the idea of like taking information and turning it into like these discrete units, 0 and 1. But actually, Shannon's great contribution to computer science is that these bits, these zeros and ones, if you assume that they are completely unreliable objects as they are, what he realizes that if you add some redundancy, some repetitiveness to these pieces of information, so like we think of information as zeros and ones, like binary, right? But if we imagine instead of having just a 0 and a 1, we make many copies. Every time your computer does a copy, every time your computer does a computation, it's actually doing this computation in a very redundant way. It's storing each piece of information many times. And what Shannon showed is that if you have enough of a redundancy in your information, your error rate can be suppressed exponentially. So he basically figured out how to take unreliable machinery and use it to get a reliable answer. And the way you do that is by copying the information numerous times, so that if one piece of the information is found to be unreliable or corrupted in some way, the final answer still emerges in a reliable way. And it's really like the unsung hero of modern computing. Without error correction, computers would not be reliable machines. And it all comes down to this idea of redundancy, just copying the information multiple times so that if something gets lost, as it inevitably does, the final answer can still emerge in a reliable way.
I guess, Mikey, one thing I wanted to ask you about, because I heard, I mean, maybe you are saying this, but I heard a slightly different story with Claude Shannon. So
Yeah.
originally, people were trying to figure out like what the best way of transmitting messages from one place to another place, and that message can be corrupted by noise, as you were
Yeah.
saying. So I think what a lot of people did was they kept sending the same message over and over again, and like you basically average it out and hope for the best. And then I
Yeah.
think Claude Shannon came and said, "Oh, you don't have to send the same message over and over again. What you can do is you can add extra bits, and if any of the bits flip, you'll know based on this message where it flipped and how to correct that itself." So is that what you're saying, or is that different from what you were saying?
It sounds very similar to me, but I think like what my understanding of what he showed is that like there's certain thing called like they call it threshold theorems. Like if you
Mhm.
send enough copies, if you send enough of these extra bits,
Mhm.
um, what you find is that the final answer has an exponential reduction in the error. I think that's sounds very philosophical, similar to what you were saying, but yeah, I don't know so much about like knowing where the error occurred. I don't know if the threshold theorems really point that out. I could be wrong though.
Yeah,
This
I
is
mean,
not a computer science.
you're adding in bits at the end, so if you know where one flips, you'll know that certain sums don't match up, and you know exactly where to fix it. For example, I like know that NASA, in order to communicate with like the satellite on Jupiter,
Always,
for every
yeah.
one bit of information they send, they have to like send 100 extra bits, 100 plus, something ridiculous, because there's so much, it's such a noisy channel. So
Uh-huh.
something along those lines. But anyway, so okay, so that's classical. Can we can we talk about quantum error correction? So we've set the stage for what error correction classically helps us do, but I guess quantum mechanically, maybe Tim, I'm gonna put you on the spot now. Where do errors come in with quantum mechanical systems, and where does quantum error correction come in?
Yeah, so we have to remember that quantum system comes with some restrictions, right? Because of this there's the no cloning theorem. You cannot just copy paste. You cannot just control C, control V a quantum bit. You can't do that. And it also means that there's no deletion. You cannot just delete. Try to delete the information. And there also and this places a severe restriction on how you do computation. But if you think of it a little deeper, this is actually much closer to the real life, right? Because real life is quantum mechanical. Like imagine it's basically philosophically it's telling you that like let's say we want to compute what happens if Tim goes to New York next week. It's basically telling you that hey, Tim literally has to go to New York to see what happens, right? Because they can't make a copy of Tim and have him walk to New York and see what happens. I mean, they could do it classically, but it would be what we call lossy. You have to like you might have to mess me up. Like I might become Frankenstein Tim, like unrecognizable, right? So this is kind of the issue of quantum computation. And one way it turns out to fix it, and I think Micah, you might be more familiar with the mathematics, is that you can't copy, you can't delete. The one way to give you redundancy is to kind of spread the information in different places. So maybe the information of Tim can be spread in 3 different places in such a way that as long as 2 of them is still uncorrupted, maybe you can recover most of Tim. Or maybe you can spread it in 5 different places, and if 3 of them are consistent one on another, you can recover Tim. So I think these ideas, I mean, linear algebra is heavily involved. When you think of it that way, it allows you to have a little resilience in quantum computation.
Anything you want to add to that, Mikey? Tim made a shout out to you.
No, I think that's pretty much it. Yeah. I guess I don't know. Like when I think about like when I think about classical computing, that's kind of how I think about it too. Even though classical computing does involve this copying, and it does involve these kind of redundant copies of the same information, in my head, I still view it as just one piece of information being spread out, even though that's not actually what's happening, because I just analogize everything to the quantum world.
I guess like so one thing I'm trying to understand is like quantum computation and using error correction. So is it like maybe it might be more helpful to describe in terms of sending a message. Like if you're trying to send a message, I assume that's also a form of a computation. So if I'm trying to send a message via quantum mechanically from one place to another place, what would like quantum error correction entail to help that message like propagate through actual space to like say get to another point?
Yeah, I mean, what? So the naive way to do it is let's say if you can take all my information, compress it in the minimum number of quantum bit and send it somewhere, right? But if you do that, well, maybe my information will get corrupted. Maybe an electron come my way and just like screw up some of my physics, right? And then you get Frankenstein Tim. But one way to do it is, quantum physics has this ability to be entangled. So you can kind of hide the information in correlations. But let's not get into it that deeply. But if you kind of break up my information into 3 places, and then send my information through these 3 different channels, maybe one of them will get corrupted, but then maybe the other 2 wouldn't. So at the end, as long as you know that it's not, as long as you know what Tim roughly looks like, you have some expectation, you can kind of reconstruct me in that way. So I think that's roughly the gist of it.
That makes sense. I guess sending different pieces of you and then if one channel gets corrupted, then with those two pieces of information, I should be able to reconstruct basically you essentially, like know where it was off. Is that fair to say?
Yeah, I
And it's
think yeah, I think for people who are more technically inclined, I mean, at the end, it's linear algebra, right? You have
Mm,
some information in some space, and you're just trying to embed it in a higher dimensional space, so that
mm,
there's redundancy in your dimensions, and so that when you send those information, you basically have to reconstruct a lower dimension object, which is a little easier and a little less finicky.
Yeah, it all comes down to all error correction, I think, just comes down to using redundant resources, more resources than are needed to encode your information, and doing it in such a way that um, if certain resources are lost, you can still recover the message.
mhm. All right. So that makes sense to me. So we've described in terms of like sending a message classically and quantum mechanically, and also in terms of computation. Now, coming back to what we talked about before about space-time itself being a computer, where does error correction come in? Like, how is that like relevant? Like, what am I trying to like self-correct against?
Yeah, I would say this is actually a lot more relevant than what people think. And this is something we take completely for granted for ordinary people, right? So
Okay.
imagine, like I was mentioned before, me just existing. Me just existing is like quantum information being sent from the past to the future, and
Hmm.
also from one space-time location to another. Of course, the Earth is moving around the sun quite fast, right? And also our solar system is moving around the galaxy. So in terms of space and time, we are traveling in space and time, and everything is traveling through space and time. And if we think of, because the universe is quantum mechanical, even though it doesn't appear so, me, you, the computer, everything we see is essentially the combination of quantum information. So how is it that we know that quantum physics is very noisy, right? There's a lot of uncertainty going on, but yet somehow we feel a consistent existence, right? Um, you can imagine a universe where gravity can introduce a lot of noise in a quantum system, and you cannot avoid it because gravity sees everything. Everything that has energy has gravity. So it has the opportunity to completely destroy the quantum system. And it turns out that the reason why things stay consistent might be because of error correction. It turns out that the way information is processed in quantum gravity may entail some kind of error correction in such a way that we don't see apparent information loss as things exist in our universe. So that's why it might be very important.
So Tim, there's a few things I want to unpack with that because you mentioned a lot of really interesting points. I guess can we start off with the notion of gravity, I guess like screwing everything up or mucking around with everything? Because I don't know, usually when I think of gravity, I think of like, things um coming together and like more in the universe, versus like the universe is expanding, spreading things out, but gravity seems to like want to bring things together. And so I'm just trying to understand from that like high school version of like physics, notion of gravity, how can we think about it in terms of the way that you just described it?
Yeah, I would say maybe that's not the best perspective. We just have to know that gravity is universal. Anything
Mhm.
that has anything, basically anything that does anything, has to involve gravity, right? Unlike
Mhm.
electromagnetism only works on things that has charge most of the time, right? But gravity is universal, and we know in quantum physics, anything that could happen has the possibility of happening. So, like
Mhm.
any atom, whatever it's doing, it has gravitational force, and gravitational force, because it's completely uncontrolled, it could just mess it up. Like the graviton could just kick it left and right and mess up your quantum system, basically.
Mhm.
Um, so from that regard, gravity is an irreducible noise in your system.
Mm. Okay, so you're saying that like we can't necessarily take it I mean, not to take it for granted that like I guess gravity can't make things consistent, is what you're saying. Or it's not the case, not necessarily. It doesn't have to be that way.
Yeah, I would say this is kind of we've mentioned a lot. This is kind of the conflict between general relativity and quantum physics, right?
Mhm.
Einstein's theory of gravity is that gravity is represented as a smooth rubber sheet. I'm sure people have seen some of the animation. And there's curvature in this rubber sheet. That's why things move and fall around, right? Everything is smooth, right? It's a smooth geometry. It's a shape. It's a shape that is that doesn't have breaks and holes and imperfections, right? But
Yeah.
quantum physics is a complete contrast to this viewpoint. We know that in quantum physics everything fluctuates. Even vacua can have particles pop in and out of existence. Things go up and down. So the quantum landscape is very rough, very noisy, right? So the
Mhm.
question is, how can something so noisy fundamentally create
Mhm.
something so smooth? That's not obvious,
Mhm.
right? And it turns out that and in fact, if you have a universe that has very strong gravity and it's highly quantum mechanical, you could just have a really noisy universe. You might have black holes popping in and out, things expanding, contracting in the blink of an eye, and
Mhm.
you will see none of that universe like what we observe today.
Mhm. What do you mean by strong gravity and strong? I mean, I guess strong quantum mechanics refers to like lots of fluctuation. But what does that mean in the context of strong gravity?
Yeah, and by strong gravity, I mean that let's say gravity is very, very, very strong. Like a little particle can turn into a black hole left and right,
Mhm.
which doesn't happen in our universe. One particle cannot make a black hole.
Mhm.
When that happens, information just jumps around like crazy. We know black holes are very good at hiding information. But in any
Mhm.
case, yeah, it is not obvious that we will have a consistent universe. But in fact, we do.
I see. I see. Also, I guess also, Tim, do you want to add to that the fragility of quantum systems, like how easily perturbed they are? I guess that comes into noise, right?
Yeah, I think Mike, you can probably you probably know a little more, but that's one of the challenges of building quantum computers because quantum systems are very frail. And
Mhm.
it doesn't mean that quantum physics is wrong. It means that quantum system is very, very hard to control. Like you have to cool a system down to very cold. And if you want to manipulate, the computer in the way that you want, you have to limit the environmental influence. Because look, the
Mhm.
environment also has a lot of quantum stuff in it, right? The air molecule
Mhm.
has quantum behavior, really. So if you don't shield your system properly, all your quantum behavior will just leak out from the system, right? It's not self-contained enough. And I think in a lot of the quantum computers we have these days, that's one of the biggest challenges, right? Like to get it to work.
Mhm.
Yeah, the biggest.
Um, okay, so I guess so I guess like to keep this continuity and smoothness of space-time as general relativity specifies, there's this error correction that comes in to essentially, I guess, um make space-time robust to quantum fluctuations. Is that fair to say? Like the macroscopic space-time?
Yeah, I wouldn't say that's the purpose of it, but I think
Okay.
this is like a recent, I don't know, in the past decade or so. This is a recent discovery that people realize gravity is structured that way. And also
Mhm.
it does it in exactly the same way that people thought of how to do quantum error correction. Basically, gravity somehow stores the information in a spread out way, such that it protects itself from its own destruction, I guess. And that's not obvious, and it's just a very intriguing discovery that gravity does that. I guess gravity is actually somewhat kind to existence in that way.
Or at least the gravity in this universe. Is
Um,
that or would you say gravity everywhere in all multiverses if you subscribe to the notion of multiverse?
Yeah, I would say gravity in all universes, such that if your gravity is weak enough,
Mhm.
it is kind to us that it doesn't destroy all the quantum system and all the continuity in the world.
So does that have to do with the strength of gravity then? Like the weaker the gravity, I mean, to a certain point, the nicer it is, or like is that not as clear?
Well, I mean, I think error correction has a limit, right? I think
Yeah.
my, like when you have too much error, at some point
Mhm.
it's irrecoverable. So
Mhm.
you can see that like space time might be fluctuating left and right,
Mhm.
but if the errors are small and coverable, then for all purposes, it might seem like not much has changed, right? And to any observer, you and I, it'll be like, oh,
Mhm.
okay, little blip here. So in some sense, you wouldn't see a glitch in the matrix if you think of it as a matrix, um,
Mhm.
unless the errors accumulate more and more and more and more. But it doesn't tend to happen
Mhm.
that way.
I see. I see.
But
Anything you want to add to that, Mikey?
No, I think that's pretty complete.
Okay. So we have a few audience questions that I just saw right now. Um, so the first one, not sure if you guys will be able to answer this one, but I guess how does quantum error correction handle aliasing, which is based on probability? So I'm not entirely sure what aliasing is. I think it has to do with like it's a signal processing term, but I'm not as familiar with that, but want to throw that over to you guys if you're
I do not know what aliasing is.
I think we'll
oh
Oh, yeah. Okay.
I think we'll pass on that unless Mikey you have something to add because
No.
yeah. Well,
Well,
for
sorry. No, I'm just Googling it. Yeah, it seems like it's misidentification of a signal frequency, which to me is just like a generic kind of error that can happen. There's distortion, there's corruption, there's erasure. Um, but yeah, all those different types of errors are handled by, at least in quantum computing, by similar error correction techniques.
aliasing is the masking of one error from another error. That's that's what the audience member has specified. Okay, I guess we can pass on that for now. And then any questions that people have that we can't answer, do ask us in our Discord, and we're happy to like engage in a longer form discussion with that. Okay, the next question is what about anti-gravity in an anti-universe? I guess Tim, I'm gonna point this question to you.
well I would say gravity is I mean if you think about gravity if you look about anti-gravity it's just gravity itself, right? I mean, you know, gravity itself can produce repulsion and attraction. Um, and if there's any concept of anti-universe, it's probably just another universe. Gravity is happy
Mhm.
to accommodate multiple parts of the universe. So I think the story will be similar. Although I don't think those terms, anti-gravity or anti-universe, are common. I don't think there are any. I don't think these are specific technical terms.
Mhm. And then I guess like in the sense for the third question is that quantum error correction would be similar there as well.
Yeah, but let me just add that like quantum physics, like the things we think of as error, it's because we're trying to do some computation and the environment is undesirable, right? But gravity doesn't really care. Like gravity doesn't have an agenda. It's not trying to compute anything. It didn't have
Mhm.
to have the structure of error correction, right? We could have lived in a universe where, you know, when an so quote unquote error happens, physics happens, right? Like maybe my
Mhm.
hand would just light up in fire one random instance. You know, nature doesn't care, right? It's just how it works. Um, but the error correction in quote, we're not nature is not really correcting anything from anything. it just so happens that the way physics works has some similarity with quantum error correction, and physicists postulate that, hey, look, that may have to do with why spacetime is consistent in that way. So just to keep in mind that quantum physics doesn't have a purpose, right?
Mm-hmm. Gotcha. So then another audience question is, I'll point this actually went to Mikey. What are the sources of errors in spacetime, quantum spacetime fluctuations?
So yeah, I think me and Tim have a different view on this. Like when people talk about errors in my view, from the perspective of physics, like Tim said though, like it's not like the universe has an agenda and is trying to do something, and there's some error in what it's trying to do. One of the things people talk about a lot is just the concept of erasure. Like suppose you lost some information. Turns out that the universe encodes things in a redundant way, to make it possible for an observer to reconstruct a certain answer to a computation if they were so trying to do so, like without the full information. Basically, you don't need all the information in the universe to see what's going on in the universe. And so I guess the type of error that technically goes under the term of erasure. Like suppose that a certain observer is just missing certain pieces of resources, that would not be enough to make the universe nonsensical to that person. So it's kind of weird. Like we talk about errors in kind of an anthropomorphic way, where like someone made a mistake or something. And as Tim said, the universe doesn't have this kind of an agenda, but it does happen to encode things with redundant resources. It's not like a minimalistic kind of setup here. So that if you were trying to do something about the universe by only looking at a certain piece of it, you would be able to do that.
And I guess I'll add that yes, I think quantum fluctuation is one of them. We don't have a theory of quantum gravity, so we don't know exactly how that happens. But if you look at specific gravitational system, you can kind of see closer where the error comes from. For example, we're not going to talk about it in this episode, but for a black hole, right? Imagine you're living in a black hole. You wouldn't necessarily know that you're in a black hole, but we know that black hole has Hawking radiation, which we're not going to talk about, but maybe next time. And that means that information could be leaving the black hole, and that could be viewed as a source of error. Like, things happening in the black hole are getting screwed up. And you buy this analogy that our universe is kind of like a black hole with a horizon, maybe information is a little bit leaving our universe too, and maybe that causes some amount of error. But somehow it's not going to be, basically information may be leaving us in the least, in the most gentle way possible. It doesn't completely destroy our universe. So at least from our perspective, that might be, what it means to have errors.
Gotcha. So we're almost at time, and so I wanted to give you both a chance to, as we usually do, as the tradition is, like, leave the audience with any parting words of wisdoms that black holes, error corrections, computation have taught you in life. I guess, Mikey, you go first. You seem most
Yeah, I feel
enthusiastic.
like we didn't really get to the meat of what we wanted to talk about today. I feel like this is one of those episodes where we like had a lot of things we wanted to talk about and ended up not. Yeah, I don't really know. How to wrap. Yeah.
What has error correction taught you about life?
To me, the presence of error correction and laws of physics, is just like another one of those intriguing ideas. Like, that there's like people have discovered this kind of analogy where you can kind of think about physics as a computation. And as we talked about many times in this episode, one of the weird things about that is it kind of makes it seem like the universe does have an agenda, right? Like it is
Mhm.
trying to do something. It's trying to protect against some kind of error. And normally we don't think about it that way. But the fact that error correction plays such a strong role in the laws of physics kind of makes me feel like maybe the universe does have an agenda, right? And so it's kind of, I mean, there's a lot of things we haven't talked about, we didn't get to, but yeah, to me, it does kind of support this simulation hypothesis in a weird way, where, you know, what if the universe didn't have an agenda, why would it use, why would it employ error correction in the laws of physics?
Yeah, and I know if some of you have watched Quadcast, you probably know my stance about the simulation hypothesis. And to put it lightly, is I think it's probably bogus, but that's not to say that the ideas are intriguing. Because the way I think about it, it's not that the simulation hypothesis is not plausible. It's that everything that we do about simulation, we copy from the real world. Like the real world is just the original simulation. I mean, however you slice it. So why have this convoluted term? But in any case, you know, this error correction bit kind of brings into focus that, like, the universe is the ultimate computer, right? We build computers modeling after physics. So maybe it's not so crazy that, hey, things we have discovered in computer science, in error correction code, you know, somehow has a role in our universe. It's because maybe from the universe's perspective, that's the right way of doing things, right? And it kind of I guess, like all physics idea, it kind of humbles you a little bit, right? Like at the end of the day, we are just a bunch of quantum information in this universe. And the fact that we exist in a consistent way, it's not obvious. It's also thanks to the universe in some ways. So I think it's interesting that we are just starting to uncover some of the intricacies of how the universe computes.
Well said, both of you. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah.
Bye.
Bye bye.